to Mrs. Fry's kitchen table physics. First thing we need to do is to make sure that we're safe. That's better. I've got my hair tied up and my goggles on, nice and safe. Now today we're going to be looking at the energy content that is stored in some different foods. So I've got a biscuit, some crisps, I've got a strawberry, not sure how that's going to work. I've got some hazelnuts and some pasta. So what we're going to be investigating is, when we burn this food, how much chemical energy is released and what is it getting converted into. So to do that, we are going to be heating up some water and seeing how much the food is able to heat up the water. So measuring the temperature change using our trusty thermometer. So for this experiment, we do need our Bunsen burner, but that's just to set light to the food samples in the first place. So you can see I'm improvising here with a bottle labelled Bunsen and a candle sticking out the end. So the first thing we want to do is to measure out 50 millilitres of water. It's really important that we keep the amount of water the same so that each of the food samples is transferring its energy to the same volume to keep that a fair test. So I'll pour that into my container. If we were in a lab, I would rather be using a boiling tube, but I'm having to make do with this glass jar. So that's my water in. So it's important, if we want to know the temperature change of the water, that we know the temperature before we start our experiment. So in this case, our water starts at room temperature, which is 19 degrees. So fill that in your tables now. And the first sample that we're going to be measuring is a sample of hazelnut. Now hazelnuts are very, very light in mass, but they actually contain quite a lot of energy. So this one is just 1 gram, but we'll see how much it manages to heat up our sample of water. Okay, so first step, remove our thermometer from the water so that we're nice and safe. Set our food sample alight if we can. Make sure not to burn our fingers. Notice I'm holding the food sample in a clamp stand.
Edit, it's clearly tongs.
And I'm going to do it over a surface that I'm not worried about the flame getting onto. So at this point, my kitchen starts to fill with lovely scents of burning food. Hopefully my husband doesn't come home at this point and wonder what on earth's going on. Okay, the hazelnut's sort of blackening without really lighting very well, so I'm not sure what effect this is going to have on our water. Hopefully some of that chemical energy is being released as thermal energy. There we go. That looks a little bit more promising. So when all of the chemical energy is being released, we'll see the flame extinguish and we'll know that all of that chemical energy has been converted into thermal energy that's then been used to heat our water. If I had enough technical expertise, I'd fast forward this section for you. Okay, so nuts are notoriously a source of slow release carbohydrate. So you can see the energy is actually being released quite slowly from this nut. It's not burning quickly, but it's burning for a long time. So nuts can help you feel really full for a long time. So our nut has burned itself out finally, and I can tell you the new temperature is 49 degrees Celsius. So fill that in your tables now. Okay, so I've just rinsed my beaker out so that it's back to room temperature, and I can put my next lot of 50 millilitres of water into my beaker. Just to double check, I'm going to take the room temperature of the water again. Whilst I'm doing this, can you predict what it should be? And actually the glass is still storing a tiny amount of thermal energy, so our room temperature this time is 20 degrees Celsius. So I think probably the next most exciting food item will be the piece of pasta. So remember, because we want to know the energy per gram of the food, we need to know the mass of the pasta before we burn it. So the mass of that piece of pasta is 0.3 grams. Okay, time to burn it. So we're lighting the sample in our trusty Bunsen burner again. Now pasta contains a faster release form of carbohydrate, so I'm expecting this to burn with a bigger flame, but probably not burn for quite as long. Get it going. There we go. Oh. It's quite difficult to get this food item lit. Those sugars are just burning in the flame more so than they're actually allowing me to release the heat. There we go, so I've got a small flame, but it is quite hot, it's quite a ferocious flame. Again, I'm trying to hold the sample a similar distance away from the beaker. And I think that pasta's actually gone out already. Yep, there's no lit flame there anymore. So if we take the temperature of our water, has gone up slightly. So the temperature of the water is now 22 degrees. Notice how short that flame lasted for there. So it's quite a different chemical energy store to our hazelnut. Okay, so we're going to try something now that contains quite a lot more sugar. We're going to see how the sugars affect the way that the item burns. So we've got a piece of digestive biscuit. Remember, first thing to do is check the mass of the item. So this piece of biscuit is 5 grams of biscuit, so quite a bigger sample than we've been using before. So you'd expect that to have an impact on the temperature change. Our water is starting again at 20 degrees. And let's see what effect this piece of biscuit has. So you will have the opportunity to do this experiment yourselves in school. And you'll notice as you're doing this experiment, you get some very, very interesting smells. The teacher that's in the lab after you will definitely be able to tell what you've been doing. Because we've got quite a big sample, we're expecting this to last quite a long time. So I'll just stop the video there and we'll resume when the biscuit's finished burning. So our biscuit ended up completely collapsing, and let's see what temperature it managed to get the water up to. So actually quite a small temperature rise for this one. It's only gone up to 25 degrees, which might be surprising considering the size of the sample that we used. Time to reset for our crisp. So you should all know the method by now. I've measured out my 50 millilitres of water. I've checked the temperature of the water, which is 19 degrees. And I'm going to measure the mass of my sample. So I've got 2 huge crisps stuck together here. So that is 3 grams of salt and vinegar flavoured crisps. And let's see what effect this has. So straight away this one started to go smoky on the outside. So it's lit really well, really easily. Let's see if it can sustain a flame for very long. So the crisp's burning really well. You can see this would be easily digested by your bodies, but it's releasing a lot of energy very quickly. See steam forming on the outside of the glass already as the water's heating up. So would you expect a big temperature change or a small temperature change, judging by what you can see? It's actually sort of sizzling, this one, from the oils I think on the surface of the crisp. Okay. Ideally I would be holding this jar with a clamp stand so that I could keep my other hand clear and safe in the experiment. But we are doing some kitchen science, so unfortunately I don't have clamp stands at home. Burning really well this one, I would expect quite a big temperature change. So remember there are 3 grams here, so if there would need to be 3 times the temperature change compared to the hazelnut for us to say that this contains more chemical energy. So do we expect it to be 3 times the temperature change? That would be about 60 degrees. Or do we think our hazelnut will remain the champion? For my finger's sake, I'm hoping it doesn't rise by 60 degrees. Alright, just got that last little bit of crisper there. And once the flame goes, we'll know that that store of chemical energy has been exhausted. You can actually see some little bubbles forming in the water, so it could be that we're actually getting to quite a high temperature of our water. We all know what temperature water starts to boil at, so if we do see some boiling, it'll give us an indication of how much that temperature change has been. Remember, it started at 20, so for it to get to 100, it would have needed to change by 80 degrees.
At this point, I really started to get worried about my fingers, but didn't really have a choice but to continue.
So be careful, you don't include too many crisps in your diet. If you do, you can see how much energy and how many calories are contained within just one crisp. Okay, that's a little bit. And our crisp has gone out. So if we take the temperature straight away, it's shooting right up. And our new temperature is 73 degrees. Oh, that is a significant change of 53 degrees from just 3 grams of crisp. So I'll just need to rinse my pot out again now. Okay, so ready for the last sample. Now, I'll be honest, I'm not sure how well the strawberry is going to burn. We don't really use strawberries when we do this experiment at school. And because there's quite a lot of water in a strawberry, I don't know if it will burn, if it won't burn, but I'm hoping that the sugar content should do something quite spectacular if it does work. So we've got our starting temperature again, and that this time is 23 degrees, so I've not quite cooled that jar down completely. And the sample of strawberry that we're going to use is £4 grams, so fill that in your tables. Now you know more or less as much as I whether this is going to work, so we'll learn some science together. Hopefully I won't set my kitchen on fire. Oh, some sizzling. Not quite a light. At the minute I think the water's just evaporating. So perhaps with a dried strawberry this would work better. I know we do have some dried banana chips that we sometimes use at school for this experiment. It is sizzling, you can't see a flame, but I think there is some form of chemical reaction taking place here. Release that chemical energy. Try not to drip boiling sugar all over my kitchen table. I think very little is happening here, so let's just see if there has been any temperature change. No, we've remained at 23 degrees for that one, so we'll call that one not successful. Okay, so that's the end of our experiment. We've tested a few different food samples and hopefully you'll be able to have a go at the evaluation questions. Thanks, see you next time.